So this will be the first lecture over chapter 16. So there'll be 3 lectures over chapter 16. So in this first lecture, we're going to cover this concept of aromaticity. Okay, so even though benzene has carbon-carbon double bonds, so it's got pi system, it's got 3 double bonds, it does not undergo reactions that alkenes undergo. So for example, we've seen several reactions of alkene, like if you take an alkene with Br2, then that'll add bromine and bromine across the double bond, anti to each other. But if you take benzene with Br2, then there's no reaction. If you take a alkene with Br2 and light, then this will do a free radical bromination at the allylic position. Right, but benzene with Br2 and lighter heat, there's no reaction. If you take a diene, as we saw in the last chapter with Br2, then that can do a 1,2 addition. Add bromine and bromine across the double bond 1,2 with respect to each other. Or it can add bromine and bromine across the double bond 1,4 with respect to each other. Or if you have something on benzene, an alkyl group on benzene, and you do a free radical bromination, then of course you can add a bromine to the benzylic position, but again, nothing happens to the benzene ring. So we've seen alkenes with KMNO4. If you remember what that reaction would do back from chapter 8, that will add OH and OH across the double bond, cis to each other. But with benzene, KMNO4 does nothing, no reaction. So, it is possible to make benzene react, but you have to use different conditions. So if you take benzene with Br2 and FeBr3, then you can get a reaction to occur. So you can put a bromine on the ring, but it's just a substitution, right? Hydrogen gets substituted for bromine, and if you notice, the benzene ring is still intact. So still benzene ring has not reacted. So there's something special about the benzene double bonds that makes it fairly unreactive, to which conditions where alkenes and alkyne pi systems would react, but benzene pi system will not react. You can make benzene react, the pi bonds react, as we'll see later, but it's not easy. Okay, so more about the structure of benzene. So 1866, Kekule proposed the structure of benzene, where it had the 3 alternating double bonds. But this presents a problem because if you had 2 groups on the benzene ring, and if those double bonds were static, then these 2 molecules would be different, right? Because in this case on the left, the 2 X groups are on sp2 hybridized carbons where the double bond is between them, and the structure on the right, the 2 X groups are on sp2 hybridized carbons where there's a single bond between them. And double bonds are shorter than single bonds, so if those molecules were static and those double bonds were static, those 2 molecules would be different. They would be isomers of each other. But there are no cases of isomerism known for benzene. So this was originally proposed as an equilibrium, where these double bonds, or these 2 molecules were in equilibrium with each other. But it's actually not an equilibrium. What it is resonance. If you remember what resonance is where you can move electrons through pi bonds, so through p orbitals, and you can delocalize the electrons through the pi system. So in this case with benzene, how many pi electrons does it have? It's got 6. And so each of those 6 electrons are equally shared amongst the 6 different carbons in benzene. So what's found in benzene is that all carbon-carbon bonds are exactly the same length. And it has 120 degree bond angles, which is perfect for sp2 hybridization. Right, so in the structure of benzene, right, if it was static, well, you have a single bond between 2 double bonds. That bond length is 146 picometers, and for a typical alkene, that bond length is 134 picometers, and what is found for benzene is exactly in the half. So it's like 1.5 bonds. Rather than a single bond on a double bond, it's 1.5 bond. And the bond length in benzene, all of the carbon-carbon bond lengths are exactly the same. They're 140 picometers. So the point is the electrons are delocalized over a cyclic conjugated system. So we can take these two electrons, move them there to make a double bond, those two there to make a double bond, and those two there to make a double bond to get the other resonance structure. And so you have to keep in mind resonance structures are not different molecules. They're simply trying to represent what the molecule looks like. So the real molecule is a hybrid of all of those structures. So sometimes, so then you could represent it like this, where each of these bonds is 1.5 bonds. Or sometimes you see benzene represented like this, with a circle in the middle, and that circle is representing what's known as the aromaticity of the molecule, that those pi electrons are delocalized through the pi system. And so that is very stabilizing. So we can get an idea of how stabilizing that is through chemical reactions. So we looked at this in the past. So we looked at this for the stabilities of different alkenes and the stabilities of different dienes, right? If you take them and do a hydrogenation, for example, if all of the products are the same, then you can measure how much heat is evolved, and that will tell you how stable one is versus another. So for example, if you take the alkene, cyclohexene, and do a hydrogenation to make cyclohexane, then that's exothermic. By 120 kilojoules per mole. And so then if you had the two double bonds, and they're not conjugated, right, they're isolated from each other, then you would expect twice as much energy to come out, and that's what you get. It's negative 240 kilojoules per mole. And if we compare these two molecules, so two dienes, and they're both disubstituted, but the difference would be these double bonds are isolated, and these are conjugated. So which should be more stable would be the conjugated one. So the conjugated one's more stable. It should release less energy when it's hydrogenated, and that's what's found. So that only releases 230 kilojoules per mole. So adding that conjugation gave it 10 kilojoules per mole stability. So what if we go to 3 double bonds? So if we had the non-cyclic system, 3 double bonds, this releases 340 kilojoules per mole. And if the 3 double bonds are in benzene cyclic, then this only releases 208 kilojoules per mole. Okay, so one double bond is 120. So 3 double bonds So you might expect you could get 360 kilojoules per mole energy out of benzene, but it's only 208 kilojoules per mole. So that's a difference of 152 kilojoules per mole. So benzene is basically 152 kilojoules per mole more stable than it should be for hydrogenating 3 double bonds. And that's significant, especially if you compare these two. Right? If you compare those two, taking 2 double bonds and putting them in conjugation, only got you 10 kilojoules per mole extra stability. But now all of a sudden, if it's 3 double bonds in conjugation and a cyclic ring, now instead of 10 to 20, now it's 10 to 152 kilojoules per mole more stable. And so that stability is due to what's known as aromaticity. Okay, so for benzene, so each carbon's got a p orbital, right? So each carbon's got a p orbital, and each p orbital's got 1 electron in it. So similar to last chapter, chapter 15, when we looked at the molecular orbitals, we could do the same for benzene. So I've sketched them out here for you already, and I put them in order of energy from lowest energy at the bottom to highest energy at the top. And so these are drawn so that if you were looking from the top down, All right, so rather than looking at the pi system from the side, you're looking at them from the top down, so that you only see one lobe of each p orbital. And so you either see it shaded or you see it unshaded, for example. Okay, so basically what we're doing, if we're letting 6 p orbitals overlap, you're basically doing math, right? So like adding, subtracting, or taking combinations of 6 different p orbitals. And then each one of them has a coefficient in front of it. So if that coefficient was 0, for example, then that p orbital would drop out of the molecular orbital. And so that'll make sense as we talk about these different ones. So the lowest one would be this one at the very bottom, where all of the p orbitals are in phase. So then so with 6 p orbitals, you're either, so rather than looking at them from the side, you're looking at them from the top, right? So they're all in phase. So you either see all open circles, or you would see all closed circles, depending on which end you're viewing from, but that would be equivalent, right? So the point is, it's represented like this, or it's represented like this. Whether you're looking from the top or the bottom, but the point is they're all in phase. So that's the most stable. And then the next energy level, you have pi 2 and pi 3, and those are equal in energy. So the word for that, they're said to be degenerate with each other. So in this case, you have 3 p orbitals in phase with each other, and then the other 3 p orbitals in phase with each other, but between them there's a phase change. So in this case there's one nodal plane, or pi 3 has one nodal plane as well. And it's just that for these 2 p orbitals, the coefficient in front of those orbitals, like I was talking about here, is 0. So those p orbitals dropped out of the molecular orbital picture. Okay, and then you have pi 4 and pi 5. So those molecular orbitals would look like this, where you have 2 nodal planes. So there's a plane there where you have a phase change between orbitals, and a nodal plane there. And then this would have 2 phase changes as well, or 2 nodal planes as well, right? One there and one there. So that's what pi 4 and pi 5 look like. And the 6th molecular orbital would be where all of the p orbitals are out of phase, and that would be the highest in energy. Okay, so how many electrons do we have? We have 6 electrons. So if we populated those, 2 would go here, 2 would go here, and 2 would go there, and that's what your molecular orbitals for benzene look like. So that's pretty complex. We're not going to sketch the molecular orbitals for all of these aromatic compounds. Just wanted to do it for benzene so you get an idea of what those look like. So there's an easier way, a method to determine the number of molecular orbitals something has and the relative energy of those orbitals, and that's to draw what's called a Frost circle. So basically what you do is you set the ring on a point. So if benzene's drawn like that, for example, we're going to rotate it so that it's setting on a point. So it's setting on a point. And if we had a circle, and then if we inscribed the benzene within that circle, then each vertice, so there's a vertice there, there's one there, there's one there, there's one there for that carbon, there's one there for that carbon, and then there's one for that carbon. So that would be the 6, representing the 6 molecular orbitals in order of stability, where you have 1 that's most stable, and then 2 that are degenerate. So that would be pi 2 and pi 3. So that's pi 1, that's pi 2, pi 3, and then pi 4 and pi 5, which each had 2 nodal planes are degenerate, and then you had pi 6. And then 6 electrons, so 2 go here, 2 go there, and 2 go there, would be a way to represent how many molecular orbitals it has and the relative energy of those orbitals. Okay, so but this is the nuts and bolts of it. If you want to know if a molecule is aromatic or not, it has to fit 4 criteria. So first of all, the molecule has to be cyclic. So that's easy to tell. Obviously benzene is cyclic, right? it has to fit what's called Huckel's rule. Means it's got to have 4n plus 2 pi electrons. Where n is an integer, so n can equal 0, 1, 2, 3, so forth. So how do you know if it fits Huckel's rule? So you take the number of electrons it has, which is 6, and you set that equal to 4n plus 2, and then you solve for n, and you see if n is an integer or not. So 4n plus 2 equals 6, so 4n equals 4, so n equals 1. That's an integer, it fits Huckel's rule. So counting the electrons, right, each double bond counts for 2, so that's 2, that's 4, that's 6 pi electrons. Okay, and then the other two criteria, it's got to be planar. That is difficult to determine, because how do you know if it's planar or not? I just gave you a molecule drawn on a piece of paper. How do you know if that's planar? Well, that's difficult. That's an experimental determination, right? And then lastly, it's got to be cyclically. It's got to be cyclic conjugated. Right, so then all atoms in the ring have to have a p orbital in order to be conjugated, right? Because if you remember what conjugation means, we talked about conjugation for that molecule, right, versus that molecule. Here you have p orbital, p orbital, p orbital, p orbital. That's conjugated because all of the p orbitals are on adjacent carbons. Here you have p orbital, no p orbital, and then p orbital, and those are not conjugated, right? So basically, all of the atoms in sequence have to have a p orbital on them to be conjugated. And furthermore, it has to be planar, because if it's not planar, right? If it's not planar, the p orbitals don't overlap and it's not conjugated. So it's got to be planar. All of the atoms have to be in a plane so that all of the p orbitals overlap with each other. Okay, so a molecule can also be anti-aromatic, and if it's anti-aromatic, then it's very unstable. So the 4 criteria to be aromatic are almost the same as anti-aromatic, or almost the same as aromatic, just one is different. It's got to be cyclic, it's got to be planar, and it's got to be cyclic conjugated, but it does not fit Huckel's rule. It has 4n electrons instead, where n is an integer. So as an example, if we take 1,3-cyclobutadiene, so how many molecular orbitals does it have? So if you remember, we can draw a frost circle. So basically take this and set it on a point, and then each of the carbon represents where a molecular orbital would be. So there's a molecular orbital at the very bottom, that's lowest in energy, and then there's 2, so that we call that pi 1, and then pi 2 and pi 3 would be equal in energy, and then pi 4, so pi 1 is going to be where all of the orbitals are in phase, pi 4 is going to be where all of the orbitals are out of phase, and then pi 2 and 3 will be in between. Okay, so now how many pi electrons? 4, right? Because 2 there, 2 there. So if you started filling in these orbitals with electrons, each orbital can only have 2 electrons. So from lowest energy to greater energy, so you would put 2 in pi 1. And now you have 2 left, but pi 2 and pi 3 are equal in energy, which means both of them will get 1 electron. And so what that means, it's predicted is that it's predicted to be a diradical species, and radicals are very unstable. It's 2 radicals and really unstable. So cyclobutadiene is not a stable molecule. It's got 4 pi electrons. It does not fit Huckel's rule, right? 4n plus 2 equals 4, so 4n equals 2, so n would equal 1/2. Does not fit Huckel's rule. It fits a 4N system instead. Right, so it's got all the criteria to be anti-aromatic. It's cyclic. It does not fit Huckel's rule. It has 4N pi electrons instead. It's planar because you only got 4 atoms. It's hard for 4 atoms that are all sp2 hybridized to not be coplanar, and cyclically conjugated. Although it tries to not be cyclically conjugated by, rather than being a square, being a rectangle instead. So it separates those 2 pi bonds to try to minimize the overlap between the p orbitals. I actually got p orbitals and p orbitals. So p orbitals all the way around the ring, but if you can stretch this bond out, then you can minimize the overlap between them and minimize the conjugation. But even so, it's still an extremely unstable molecule. It's been synthesized, but it's been synthesized in a frozen argon matrix at negative 189 degrees Celsius. And if you warm it up much above that, it'll decompose. So anti-aromatic molecules are very unstable. Okay, so how about 1,357 cyclooctatetraene? Is it aromatic, anti-aromatic, or non-aromatic? So we've talked about aromatic and anti-aromatic before, and we'll talk about non-aromatic. Well, so first, easiest thing to do, first of all, is it cyclic? Obviously it's cyclic. You can't tell if it's planar or not, because you need to figure that out experimentally, but you can easily determine, does it have the right number of electrons or not. So you got 2, 4, 6, 8 pi electrons. Does that fit Huckel's rule? So 4n plus 2 equals 8, 4n equals 6, n equals 3/2. That's not an integer, does not fit Huckel's rule. It fits 4n system, right? So it fits a 4N system. That means if it's conjugated and it's planar, then it's anti-aromatic. But it doesn't want to be anti-aromatic because that's extremely unstable. So if we drew a frost circle for it, so if we took this and set it on a point, right, then pi 1, pi 2, pi 3, that's 6 electrons, it's got 8, so the next 2 would have to go here. So it would have to be a diradical species if it was anti-aromatic, but it doesn't want to be anti-aromatic. And the point is here, this ring is big enough that it's floppy, and it actually exists as a tub or a boat conformation. So it's not planar. So it does not fit that criteria. So it's neither aromatic nor anti-aromatic, it is simply non-aromatic. So that analysis is not right because it's not planar, it's simply non-aromatic. So what does that mean? That means these double bonds are going to behave just like normal double bonds, and cyclooctatetraene reacts like normal alkenes do. So the reactions that we looked at in chapter 8, this molecule would undergo those type of reactions. Okay, so basically what you'll have to do in this chapter is look at molecules and determine, are they aromatic, are they anti-aromatic, or are they non-aromatic? And if a molecule is cyclic and has the right number of electrons and is conjugated, it will want to be planar if it can, so that it can be aromatic. Right. If a molecule is cyclic, where did this go? Sorry, that was it. Yeah, if it's cyclic, has the right number of electrons, and is conjugated, well, they will want to be planar so they can be aromatic. If it's cyclic, has the wrong number of electrons, it will try to not be planar so that it cannot be anti-aromatic, as we saw with cyclooctatetraene. Okay, so just some more examples of aromatic compounds. So we looked at benzene. This compound is called naphthalene. So obviously it's cyclic. All of the carbons have a double bond to them, right? Every single carbon's got a double bond, which means all carbons have a p orbital. So if this has the right number of electrons, it will want to try to be planar if it can, so that it can be aromatic. So how many electrons does it have? It's got 2, 4, 6, 8, 10, because each double bond counts for 2. Does 10 fit? 4n plus 2 equals 10. So 4n equals 8, so n equals 2. That's an integer. Yes, this is an aromatic molecule. Anthracene. So again, all carbons have p orbitals because all carbons have a double bond, so they're all sp2 hybridized. It's obviously cyclic. You got p orbitals going all the way around the ring. Does it have the right number of electrons? Well, you got 2, 4, 6, 8, 10, 12, 14. Does 14 fit? Huckel's rule. Just set that equal to 4n plus 2, solve for n. N's an integer. Yes, that fits Huckel's rule. It's cyclic. All of the carbons are sp2, so it's got p orbitals all the way around the ring. It's conjugated if it's planar. This is a flat molecule. This is also aromatic. This molecule is called anthracene. And so these are some other examples. Pyrene, that's an aromatic molecule. Phenanthrene, benzoalpha pyrene. If you went through the analysis, you would find that all of these have fit Huckel's rule. All right, so if we just did that here, that's 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Did I count right? 5, 6, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. What did I do wrong? 5, 6, 7, 8, 9, 10. This is not working. I will have to look at that. These others for sure are aromatic. Let's see, 1, 2, 3, 4, 5, 6, 7, 8 double bonds. That's 16 electrons. What is wrong with this? Okay, so this is what's wrong with this. So, that part of the molecule is aromatic. This molecule would be somewhat reactive at that position. You could do the same thing here. Right, molecule, part of the molecule can be aromatic and the other part non-aromatic. This would be a fairly reactive molecule as well. And a lot of these molecules are fairly reactive. They're carcinogens. This particular one is a carcinogen. It's formed during the incomplete combustion of organic matter. So cigarette smoke can contain this molecule, and it can have it can be carcinogenic. But these other molecules are, without question, the entire ring is aromatic. The entire ring here is aromatic, right? That's 2, 4, 6, 8, 10, 12, 14 electrons, and 14 electrons fit. So 6 fits, 10 fits, 14 fits, and so forth. Okay, so lastly here, fullerenes are relatively new allotrope of carbon discovered that are aromatic. So it's all carbon. So it has a soccer ball pattern. So this is Buckminster fullerene or buckyball, or sometimes called C60. So it's 60 carbon atoms, but it's in a sphere, and it's got a soccer ball pattern. So you got 6 and 5 membered rings in a soccer ball pattern. All of the carbons are sp2 hybridized, and they have aromatic properties to them. So pretty interesting molecule, right? It's a sphere, but it's all carbon atoms. And so you can put things inside that sphere, but they have interesting electrical properties in general. Or you can put them in tubes. You can make what are called nanotubes. So these are, again, just these benzene rings in a tubular form. And because they're big enough, then you can have conjugation between the p orbitals, so they have aromatic properties to them. Okay, so we'll stop there, and then in the next lecture we'll look at more examples of aromatic molecules.